Okay, I found the final version of the code that I used, and I produced all of these animations really using very similar code. You'll see I have here them lined up. The Galilean Transform looks like this with the straight lines coming across. Basically, in the view of Galileo and most people today, really, time, the current time, is a universal thing. So if the time here is now, then the time here would be now also. And that doesn't matter how fast you're moving. And so basically that's what all these lines represent. These horizontal lines represent events in space that all happen at the same time. So that's the Galilean Transform. The Lorentz Transform is a bit different. So we might consider all of the events on this line to be at the same time, but if we accelerate to a different velocity, then we would see different events being at that time. Okay, then we have a rotation transform, which is really not a space-time transformation, but just a space-space transformation. Basically, when you turn around, the x-coordinate becomes the y-coordinate. Your left becomes your forward, and your forward becomes your right. And anyway, so that's a rotation transformation is generally what you see when you're converting a forward to a left or a forward to a right as you rotate. So that's not a space-time transformation. It would look more familiar. This is more of a these Galilean Transformation and the Lorentz Transformation are of course more mathematically based, because generally we cannot see space and time transforming in this way when we accelerate, but this is what it would be. Of course, if this actual Lorentz transformation has this origin right here, which represents here in a point in time and space, and of course, in reality, we're not going to be able to accelerate instantaneously. So I also have this Rindler thing, which kind of just moves that center line, that center point off to the side, and you can see if you went far enough to the right, then these, and just zoomed in on a little portion of this, basically the time would appear to be traveling more or less linearly, and this might be an object of a particular acceleration, and I'll try to explain that in more detail sometime when I'm thinking about it a little more clearly. Anyway, what's interesting about the different animations that I've shown you there, they all come from the same code, and it's a fairly long piece of code, but what's kind of interesting about this piece of code is how little there is to change between them. And right here I'll show you these lines up at the top. This little switch right here at the top, I said type equals Rindler because I wanted to create the Rindler animation. And what it does, it goes through switch type, and for the Galilean transformation, it basically says GTFX. I wish I remembered what that stood for, but apparently I do have these different functions on each of them: GTFX, GTFT, GTFX, GTFT, and this is what changes in the code for the different transformations. In any case, this equation basically says that x prime equals x minus vt, and t prime equals t. In a Galilean transformation, you're basically all of the events basically move so that they're given a certain velocity. So the objects that are moving at that new velocity, or at your new velocity, once you accelerate to them, they look like they're standing still. So that's why this. So they would be standing if they were traveling originally at velocity v, and this would make it so they were standing still at position x. And t prime equals t would just mean that your object was the event stays at the same time. It doesn't change what time it is. This formula here is the rotation transformation. If you're familiar with what is it called? Transformation matrix, maybe. This may be familiar to you. You can see down here examples in 2D graphics, rotation, and that's what I'm looking at. X prime equals cosine theta times x plus sine theta times y, if you know how to do a matrix multiplication, and y prime equals negative sine theta x plus cosine theta y. And in fact, that is exactly what is right here. X times x equals x cosine theta, or x prime equals, let's see, actually I guess it's t rather than, anyway, it's x times cosine of v, and t times sine of v, minus sine of v. So the signs are maybe a little bit off from what you're used to, but it's because it's a rotation, maybe a rotation in the opposite direction, or the coordinates are, I'm using our x and y instead of t and x, and they're in a different order. But anyway, this is basically that rotation matrix that is up there on there, and so this is the rotation matrix, and that's all that's changed between those two animations. This animation keeps does the transformation that keeps the line straight, and this transformation does the rotation transformation. And everything else in the code is identical. The fading in and out of the blue lines, basically they start with a perpendicular set of axes, and then they fade out as the transformation is applied over and over and over again. So in this one you can see kind of the yellow originating over here, turning over and coming over, and floating over there and fading out again. And so it's just that same transformation being applied to that, what starts out as a perpendicular set of coordinates, and then it just leans on this one. The Lorentz transformation is very similar to the rotation transformation, except you kind of replace these cosines and sines with hyperbolic sines and cosines. So here you'd have let's see, x and t. We can make the matrix would look like xt, and it would be cosh v and negative sinh v, and then this negative sinh v is multiplied by the x. I'll put that one first. Negative sinh v and cosh v. I put it that way because it's a little bit easier to remember this kind of the symmetrical way of matrix multiplication than it is to remember it as two separate lines. In any case, once I've got those those different transformations, pretty much everything else is identical. You can see some things are a little bit different. For the rotation, to get everything to look right, I picked a pi over 12 as the velocity increment, whereas for the Galilean and Lorentz transformation, I just had the velocity increment as 1. it might be a good idea to lower these to make the animations look a little bit nicer, being as these slopes are actually changing really kind of fast, and maybe it would be nice to kind of have them slowly scoop over here. I think I chose it this way though because making it move very slowly would have created a file that takes a really long time to download. As a GIF that would be true, but if I'm making a video of it, that changes things, doesn't it? So what I'm trying right now is to see just how well designed this code is. I just changed this v increment from 1 to 0.1, and notice I put the type equals Lorentz up here. And right now I'm waiting because you see it's running up here, and hopefully it doesn't crash my system in the middle of my video. That would be bad. Now what was 5 or 10 minute wait for me was fairly quick for you, the viewer, through the magic of recording a screen capture. On the other hand, this is not exactly the result I was expecting. It's a little bit hard to exactly describe what I'm seeing here. Yes, it is going 10 times as slow, but it's also brought the particular lines 1/10 as far apart, so we're not seeing the entire picture. We're seeing just a small portion of it before it fades away. So maybe if I could do something with the fading. On second thought, I don't think this fading is going to do anything. What's going on is the v increment affects both the speed of the rotation of the thing and the distance between, like, the red, orange, yellow, green, blue, violet lines. So what I would need to do is make those two separate variables, because I kind of want the spacing between those lines to be more, but I want to keep this slower speed. Unfortunately, I'm going to have to put that in a later video, because otherwise, after about 10-12 minutes, these things start to lose their sound timing. So we'll make that into another